All right. Hello, everyone. Welcome back to Fundamentals of Nano and Quantum Photonics. So, in the last week, that was week 9, we talked about what are the necessary conditions for studying quantum nature of light. We introduced the idea of photon statistics, and then finally towards the end we spent some time on trying to introduce the second order correlation function. And I think I was a little bit rushed towards the end, and I guess there are some questions about it. So let's just talk about the second order correlation function one more time. And then after that, I'll later in the week, I'll introduce the idea of coherent states. Okay. So before we go into that, so this was what we were discussing last time. And I think one of the main questions was, at least the definition was, I believe, clear, right? So definition says that it's a second order correlation function. So you have, let's say, an intensity, and then there's another beam with an intensity t plus, which is delayed, so t plus tau, and then the average intensities, right? So you remember the experiment wherein we had interferometer, correct? The beam is split into two parts, and then one of them is delayed with respect to the other, right? So now the question was, I think, for some of the students, it was not very clear why the G2 function goes above 1 in the case of chaotic light and not in the case of coherent light, right? So let's try to first talk about coherent situation, okay? What do I mean by coherent light? I mean that I'll have a light beam with intensity of this fashion, I naught, let's say exponential I omega t. So it's a particular frequency and it does not have any change in amplitude. The amplitude is fixed or constant, correct? When you have such a beam and you take it through an interferometer, so remember what the interferometer was this way, right? So you have a beam that is first going into the first PMT and the second PMT, and one of the second PMT is delayed by a delay. So that's why you have the product of currents, right? And we said the product of currents is essentially proportional to the product of intensities. That was the premise of this. So now what will happen to the correlation function when I have this monochromatic wave with a constant intensity? Obviously, let's say since it's a constant intensity, the interferometer will not know the difference between the original beam and the delayed beam, right? So the product is always going to be the numerator here, since I of t and I of t plus tau is going to be simply I of t whole square, correct? That's it, because there's no difference in amplitude and it's just a phase factor that comes in, correct? So if you calculate this, you will quickly see that G2 of tau is going to be 1 for all tau, right? So this is for a monochromatic wave. Is this part okay? Are there any questions in this? No, right? So basically it's a constant intensity, that's all we're saying. It's an intensity correlation function, and if the intensity is constant, the correlation function is going to be 1. That's it. There's no big surprise there. Now what happens when you have a chaotic light? Oh, yeah.
Constant intensity being split, like a monochromatic wave being split into. So shouldn't there be interference patterns?
Okay, the question was very interesting. So we are talking about a constant intensity wave that is getting split into two parts, right? Monochromatic wave. So shouldn't there be interference pattern? But remember what we are actually trying to measure. We are not interfering the beams. Okay, if you go back and look at my interferometer here, you will see that you have one beam which is falling on a PMT here, which is a photomultiplier tube, which is a very sensitive photodetector, and the second beam also is falling on a photodetector. And we are not really interfering these two beams. We are only looking at the photocurrents. And all we said was the photocurrent fluctuation is going to be proportional to the incident intensity. So we are not really interfering the beam, so there is no reason to think that there should be, or rather we can think that they can be interfered, but it will not happen, right? It's a valid question, but you will not have that scenario, okay? So now what happens if in the case of a chaotic light, what happens? What do I mean by chaotic light? So I mean that, let's say this case, let's say we have an intensity I of t of the form some average value plus delta I of t. This is my intensity. What do I mean by this? If I were to draw the intensity, if I try to draw this, let's say as a function of time, this is my t and this is my I, right? So I'll have a certain mean value here, let's say some mean value, and then the intensity of light is simply fluctuating around this, some random fluctuation. So this is my average value I, and that I'm representing in the angular brackets, and this is my delta I, and it's actually exhibiting is a function of time. The average value is constant, let's say, but there is some fluctuations in that. If you consider the initial case wherein we had a monochromatic wave, we assume that this I naught is a constant. So if you were to draw this, you would simply draw it as a function of time. The amplitude is constant. So you take the modulus of it and you will see that it's a constant, right? A coherent beam will be like this, a flat thing. But a chaotic beam is some fluctuations are there, random fluctuations that I am representing as the mean value plus delta I of t. These fluctuations, right? Now what will happen to the correlation function in the presence of these fluctuations? So I did this derivation partly last time, but let me just repeat this section of it just for sake of clarity. Okay, so now what we are interested in calculating is the numerator, which is I of t times I of t plus tau, right? If we were to calculate this, quickly we'll see that this is simply going to be average of two terms, I of t, instead of this, I will write it as mean value of I plus delta I of t. This is the first thing. And the second part is again mean value of I plus delta I of t plus tau. These are the two things. So I can multiply, take products. So essentially what I'll end up with delta I whole square plus delta I into I plus I into delta I of t plus tau, plus the fourth term will have both the deltas. So delta I of t into delta I of t plus tau. Okay. This is my terms, right? So quickly I'll see that what is the average value of this function here? If I have some fluctuations, what is the average value of delta I? 0. Because it's a random fluctuations. If I have delta I like this, all of them will average out to be 0. So basically delta I average, or even if I want to explicitly say it, delta I of t average is equal to delta I of t plus tau average. That's going to be 0, right? So my numerator is turning out to be having two parts. The first one is basically, this whole thing is basically delta I square plus delta I of t into delta I of t plus tau. These are the two terms in my numerator, right? If I substitute it back into the correlation function, what will the correlation function become? Essentially it will be mean value of I divided by mean value of I, right? Or rather, yeah. Now the central problem will become what happens to, let's look at it this way. Delta I of t into delta I of t plus tau is how much? That's the main thing we have to think about. So we will take two scenarios. The first scenario is when tau is much greater than tau c. Tau much greater than tau c. What does it mean? If you have the fluctuations, the time constant, the time delay is greater than the coherence time, do the fluctuations in one beam have any correlation to the second beam? Right? So essentially what we said was, This delta I represents these fluctuations. Now we are saying that the delay is greater than the coherence time. If the delay is greater than the coherence time, there is no way these fluctuations have any correlation with the delayed fluctuations, right? So then basically you have two random fluctuations. Product of two random fluctuations. The product of two random fluctuations is going to be another random fluctuation, right? So basically delta I, if you want to explicitly say it, delta I of t and delta I of t plus tau have no correlations, right? Implies the product of those fluctuations, averages to 0. Okay. If you have long time, right? So now, and then basically, so you will quickly see that g of t is going to be equal to g of t tau much greater than tau c is going to be 1. Correct? Because the first term anyway is just simply I of t into I of t plus tau, if you want to write it like that. Okay. Explicitly, if you want to mention the time averages also, this guy is going to be I of t average into I of t plus tau, the product of averages. So that's going to be 1. Okay. This is the first scenario. A more interesting thing happens when your tau is close to 0. Tau equal to 0, let's consider. What will happen now? When tau is equal to 0, is there any correlation between delta I of t? So now delta I of t and delta I of, again t, right? T plus tau, but tau is 0. So delta I has perfect correlation with itself, right? So in this case I can say that you have delta I of t has perfect correlation with itself. So what happens now? Think of it like this. Let's say you have some fluctuations which are averaging out to be 0 in the first case, right? This is averaging out to 0, right? But now when you take a product of two of these fluctuations, what will the fluctuations be? No, the fluctuations will all be positive, right? So this is basically, if I can write it, this is delta of I of t. The second case is delta I of t whole square, right? It's a product of fluctuations into delta I of t. When you have product of fluctuations, they'll sum up to non-zero value, correct? Whereas in the first case, if you just take the average, if it's uncorrelated, they'll sum up to 0. The mean value will sum up to become 0. But if you have correlations, then it will be non-zero value. In here, it will become basically, in this case, G2 of tau is going to be 1 plus some delta I of t whole square. In the case, and then, oh sorry, if I want to write it as just in terms of t, I'll write it as this, t plus tau average divided by delta I of t, sorry, average of I of t, average of I of t plus tau. Okay. So this is always going to be greater than 1. This is G2 of 0 greater than G2 of tau greater than tau c. Okay. So at 0 delay, you see that the delay, this increases the fluctuations. Okay. You see, you follow this? So now that's why we have, if you have a chaotic light, again, I mean, if it's a normalizations, it can just go to 2 or slightly more than 1 and all that. It depends on what kind of normalizations you are using, what definitions. But essentially the important point is that if you have chaotic light, you will get G2 of 0 greater than 1. If you have a coherent source, you will have exactly 1. So, right? This is what we discussed last time, but I just thought that I'll take some time to explain it one more time so that it's clear. Yeah. So basically the question was, if you are saying that coherence time is if you look at a light from, let's say, some source like a sodium vapor lamp or something like that, the coherence time is very small because you have, let's say, too many atoms emitting, and the coherence time is very small. So will you see this G2 function greater than 1? Yes. So basically just that, if your coherence time is small, then basically till that time only you will see some G2 of tau greater than 1. Above coherence time it will be it's uncorrelated completely. It should be 1, that's all. Any equivalence for spatial correlations? You can actually do it in time, space also. It should be there. There should be some correlations. So if you look at now, if you think about it, the equivalence in terms of space, over a certain length, you will have coherence. That will be coherence length. If the length is less than coherence length, you will definitely see that it is correlated.
But then it won't be the same experiment.
It will not be same experiment, that you don't have a delay. You have to move the position. In position you have to move. In this experiment, no? Here I said originally the intensity interferometer experiment in terms of actually the astronomy case was actually moving this. You look at light from particular star, you put 2 mirrors, sometimes even half a kilometer apart. Collect the fluctuations and then see them. And you move the mirrors close and far and all that. So that was the original experiment. Okay. So large distances so that you actually, because you're looking at light years away, right? And you're trying to determine the size of the stars. So it's pretty involved, but okay, anyway. Okay. So this is about the classical case. So far, we have not talked anything about the quantum picture, right? We just considered the electromagnetic wave with some intensity and some fluctuations. But now what happens when you have quantum source? Okay. So what happens when you have, let's say, a stream of photons? We can consider 2 scenarios here. I'll call them as, the first one I'll call it as a bunched source. Basically, what I mean is the photons are bunched together and they're coming in packets. Okay. In the other way, I'm calling it as coherent source. Sorry, the diagram is not very clear, but essentially what I'm trying to say is you have average number same, but then there are some random, the point at which the photon comes is random. We talked about it in the case of even the photon statistics, right? Poissonian case, where there is a certain statistic, there's a mean number of photons, but then the fluctuations are actually going to be equal to the average number, right? The standard deviation is basically the square root of n bar. So that is the case, coherent source, right? So now what happens if such a stream of photons is incident? Now, instead of my classical, Hanbury Brown-Twiss interferometer, we'll consider a small modification. So now I have my stream of photons coming in onto a beam splitter, which is splitting the photons. And now the outputs, these are actually single photon detectors, or rather, PMTs and things which generate basically a photon counter, you could call it. It generates a pulse whenever you have a photon incident. One photon also will generate an electrical pulse. So now you connect them in such a way that you take it to a timing electronics board, wherein whenever there is a pulse on D1 here, the photon is coming into detector D1, the pulse goes to the start trigger of the counter. So the counter starts counting how much time. So this becomes the t equal to 0. And now if a second photon comes on D2, it stops. So what effectively it is doing is the counter starts measuring time when start pulse is generated. When is the start pulse generated? Whenever a photon hits D1. Okay. Now, if another photon hits D1, nothing happens. The counter has already started. It will start counting and it will stop only when D2 pulse is generated. Second photon hits stops counting when D2 pulse is generated. Right? D2 is connected, so it will stop counting. So now it will tell me what is the time delay between these pulses. Okay. So now what I'm saying is, let's say I have a stream of photons. I'll consider, let's say first photon comes at some, let's say 1 nanosecond. Okay. The photon has come. So the detector will start measuring. And the next photon comes in D2 at, let's say, 1.3 nanoseconds. So the counter tells me delta t. Delta t is going to be now 1 and 1. So 0.3 nanoseconds is my delta t, right? between the start and the stop pulses. Now another photon hits and then the detector starts counting again. Now the delay between the pulses delta t is now maybe 1 nanosecond. Then it can be 0.5 nanoseconds and so on. So basically for every set of photons, you are getting a delay between the photons. When you get such a delay, you build a histogram out of it. Okay. So basically in this case, what we are building is on the y-axis, on the x-axis, you have the time interval. Let's say in this case, what this is telling us is there is, 1 nanosecond, maybe it's not nanosecond, whatever, let's consider nanoseconds. 1 nanosecond, you have some counts, 2 nanoseconds, same count and going on. Okay. But in this case, schematically, I'm saying that at 0 nanoseconds, when there is no time delay, you have a very large count. But once you cross a certain threshold, you are seeing that count is more or less uniform. Okay. Now, why will this distribution occur? That's a question, right? So now let's consider one by one. What happens in the case of, let's assume, is this part clear? The histogram part. So what is a histogram? Essentially, you have a stream of photons coming in and then it is hitting the photodetector. Whenever a D1 pulse comes, we are starting the timing, and then stop button we are pressing whenever D2 pulse comes. That's it. The distance, the time delay between them, we are building a histogram. Keep measuring the delays, delta t's over millions of pulses, and then you get a nice histogram. That's all it is. Okay. Is it difficult to generate a histogram for million pulses? No. If you have a pulse rate of, let's say, 1 megahertz, that's enough. We can generate within 1 second. I'll generate 15, at least 500,000, delta t's, right? Like that. Okay. Now let's consider what happens in the case of bunched light. Okay. What I call as bunched here. Okay. Physically, the photons are like this, right? Now, let's say one photon has come. The first photon has come here. The photon has equal probability of going either to D2 or D1. 50-50 probability. It can go either way. Let's say it went to D1. It starts counting. Now the second photon comes. It again has an equal probability of going to D1 or D2. They are not related, right? So let's say it went to D2. Now you found out the delta T. Correct? Similarly, you can construct. Suppose first photon comes to D1 and the second photon also comes to D1. Nothing much happens. If the first photon goes to D2 and the second photon comes to D1, after the second photon it starts counting. The first photon is ignored. There's nothing to stop. First photon is ignored. Only when it starts counting, right? So in a way, this basically this counter is measuring the conditional probability. Conditional probability of photon arriving at time tau, provided a photon has come at, photon is incident at t equal to 0. At time t equal to 0, we have one photon. After that, at some tau, what is the probability of finding a photon? That is what this histogram represents. Okay. Now, if you have bunched light, lots of photons coming in bunches. Okay. So quickly you will have one pulse coming in, immediately second pulse can come into D2. So the count is high. Okay. Immediately the second photon can come, right? Maybe the second photon went here, but the third photon will go to D2. But at very, very short time intervals, you have much higher probability of finding a photon. Okay. That is why in this picture here, whatever you are seeing, this is basically histogram for bunched light. When I say bunched light, I mean the photons are very close to each other, right? There are time gaps in between where, there are no photons for a long time. It's all right. Okay. Another way of thinking about it is, think of a scenario where the photons have a very long delay between them. Maybe 10 nanoseconds between them. The first photon comes, starts. And then second photon comes at 10 nanoseconds, something. Second photon comes at 11 nanoseconds, 12 nanoseconds, and so on. There is no, it's equally likely. It's a random process. The photon, when it comes, is a random process. So you can at larger times, right? You have no, there's equal probability of finding two photons separated by delta T. Right? Because when you are looking at a small time gap, the photons are bunched. But if you look at long time intervals, you'll find some photon for every set of time intervals. You'll find something. For 10 nanoseconds time interval, 11, 12, 13, you will find. So that is why over a long time the probability, the distribution is becoming, the histogram is becoming flat. Only when you have short time interval, you have a larger probability of finding photons. Okay. So this is a histogram for bunched light. Now, how will the histogram look like when you have coherent light? The coherent light, the difference is that there are some fluctuations, but the positions are random. That's it. There's this average number of photons is maintained. In the case of bunched light, if you go to finer and finer time intervals, you see that the probability is, average number of photons is higher here, right? Or rather, yeah, if you take 1 picosecond, right? It becomes very, very, you can have higher probabilities. Again, there is difference in the probability of finding photons. But in coherent case, the probability is constant. The average number of photons is constant. And then there is some randomness. Okay. So because of the randomness, if you look at the correlations, the first photon comes starts and the second photon comes starts. So we can never predict where exactly is that random. So for any set of time intervals, delta t, there is an equal probability of finding a photon. Or rather, yeah. That's why if you have a coherent light source, okay, now if you have this time interval and you have this number of events, these are truly random events. So for any set or for any delta t, you will have equal probability. So you're essentially having a histogram like this, constant. There is no change. If you have a coherent source, the histogram will be flat. When you have a chaotic light bunch source, you will have this coming higher. Okay. Okay. The question was, if you have waves, we understand coherence. We can talk of the fixed phase relationship between, let's say, 2 points in space. That's a coherence length. That the maximum length over which you will have fixed phase relationship is the coherence length. Okay. The maximum time over which you will have a fixed phase relationship is coherence time. So what we said was, if you know the wave at the point, let's say t1, you can calculate what's the wave at point t2, provided the time gap delta t is less than the coherence time. If the time gap is more than the coherence time, then there is some fluctuation, and then there is an unknown amount of the wave becomes unknown, right? So there is no mathematical way of calculating it beyond the coherence time or even the coherence length, right? That's what we discussed. So now what we are saying is, the question was, what does it mean in the quantum picture, right? So remember when we talked about the statistics, right? We considered a perfectly, a monochromatic wave, right? With constant intensity. But only that the photon is unknown. The number of photons, average number of photons is same. But then if you keep finely checking it, initially start measuring with, let's say, in a 30 centimeter beam length, you check how many photons. In a 2 centimeter beam length, what will happen? And then 0.2 centimeter, what happens? So basically the average number of if you keep checking like that, there is a discrete number of photons, correct? Initially we took the example of, I think, 3 photons in a 30 centimeter length. So now these 3 photons are occurring at 1, 2 and 3 positions. But now when I go to 3 centimeter blocks, I'm making 10 measurements. In 3 of those measurements, I'll find a photon, and another 7 of them, I don't find a photon. So intrinsically, because there is no way for us to know what are those time instants where the photon occurs. The photon, even if you have a coherent beam, constant intensity and so on, if you take long enough time, everything is mean number of photons. But because of the discrete nature of photons, you can't think of, let's say when I started with 3 photons in 30 centimeter, right? 30 centimeters, 1 nanosecond. If I make a measurement in 1 picosecond, I'm subdividing it into 1000 measurements. In those 1000 measurements, if the average is like, let's say 3 photons, if I make 1000, 0.003 photons, I can't have 0.03 photons in every of those measurements. So I'm going to have only 3 measurements where the photons will be detected. In every other measurement, there is no photon. So essentially, the discrete nature of the photon is causing some fluctuations in the photon number. right? And that's what we said is it's a Poissonian process. So the fluctuations is simply going to be square root of n bar, whatever, average number of photons. So even for a coherent beam, it will happen. It's just that you keep going into smaller time intervals, you will see that, just because it's a discrete nature, right? So, I mean, there is some relation between that and this, but there also you might say, we looked at the G2 function, and G2 function was greater than 1, equal to 1. Coherent is 1 and G2 is looking more than 1, right? So automatically you can, I think, guess by now where will I go next. So I'll go to Sub-Poissonian case and I'll say that it will be less than 1. But these are not exactly identical. There is a subtle difference. But right now, most often you will find the case that if you start measuring the beam statistics or the photon statistics, if you get a super Poissonian, you will end up getting G2 more than 1. Usually you will find that there's a subtle difference. But okay, did I answer the question? The question was about what is coherence? What does it mean if you have coherent light? Yeah, it's basically sort of a uniform number of photons are coming.
But they are random.
They are random. The position is random. There is some amount of fluctuations. You can think of it like that. Let's say if you take beam segments, right? If I take any set of beam segments, I'll find average number to be same. The same length of beam segments. But if I take a bunch, let's say, if I take 130 centimeter block, I might find 10 photons. Next 30 centimeter block, I might find only 5 photons. So they are bunched together. But if I take any 10 centimeters, did I say? Yeah, 10 centimeter blocks, beam lengths, I'll find in a coherent beam, I'll find the same number of photons. Any 10, choose any distance.
But only the position will be random.
The positions are random. I cannot predict. Okay? Okay? Of course, if you go to long enough thing, you will see that it average out again. Anyway, okay. So this is about the HBT experiment with the coherent and bunched light. Yeah. So this is the G2 function. Again, it's in a way second order correlation function only we are measuring, but differently we are measuring, right? Yeah. So now the third case. What happens if you have? So we have considered back the bunched case, the coherent case. Now we'll go to the third case, which is essentially the uniform distribution of photons, precise distribution. So what will be the photon statistics in this case? Anti-bunched, what will be the photon statistics? What will be delta n in the case of precisely 0, right? Delta n is 0 because they're precisely coming at a particular point of time. Now, what will happen to my G2 function if you have this scenario? Now think of my interferometer again. So let's say there is this beam splitter and there is G2 here. Sorry, this is my D2 and this is my D1 here, right? This was I'm just leaving everything else. So now let's think of it. There's a photon coming here. The photon has gone to D1. What is the probability that the photon goes to D2 at the same time instant? Tau equal to 0. 0. If the photon has gone to D1, it cannot go to D2. Right? But then if you, of course, this is never going to be perfectly anti-bunched. If you have perfect anti-bunching, it has to be 0 at G2. And then you keep measuring that over different time intervals. You will see that the histogram turns out to be different. If you measure a histogram in this case, let's say this is my time, let's say tau. If you are measuring over large gaps, there's an equal probability of finding. But once we come to close enough time, the probability has to go to 0. Basically, this is my G2, right? Number of counts is essentially proportional to the correlation, essentially. So this is going to be G2 of tau is going to be ideally 0 at tau equal to 0. When the delay between the detectors is 0, ideally you should have 0 counts. But then if you take larger delays, then there is initially there will be some increase, but then it will come to a finite probability. If the delay is very large, you might say if I take perfectly anti-bunched case, it should not happen. But of course, you're going to have some variation and there is no, it will essentially become 1. Okay, large number of 1 nanosecond, 2 nanoseconds and so on. You keep measuring. Okay, ideal case you can think of the photons coming at, let's say, 10, 20, 30 nanoseconds and so on. Or let's make our life simple. Let's say every nanosecond there is a photon coming in. 1, 2, 3 and so on. 1, 2, 3 and so on. Okay. 4, 5 nanoseconds. Now the first photon has come at 1. Second photon has come. Okay, at time 2 nanoseconds, you should definitely find. So you'll find that. But then again, if you go let's say by chance this is missed, 2 is missed. 1 and 3 you will find 2 nanosecond spacing, 3 nanosecond spacing, and so on. So basically there is equal probability of finding that. Okay. See, even if I say anti-bunched, now the question is, perfectly anti-bunched it won't happen. But you can always have a scenario where, let's say, this photon is missing, these 2 photons are missing. Remember, we are talking of millions of photons coming in, right? If just 2 photons are missing, then the time gap is what? In my analogy, this is the time gap is 2 nanoseconds. In this case, 3 nanoseconds. I can even have 5 nanoseconds gaps. But basically equal probability. It's still anti-bunched, because if you look at the fluctuations, delta n is still less than average number of photons. I can immediately think of such scenario. So basically G2 function goes to 0. Okay. So this is a very interesting way of classifying. So we talked about classifying light based on Poissonian statistics. We said that we have Super-Poissonian, Poissonian statistics, which are classical light sources. The Sub-Poissonian, we said that we cannot explain by classical theory. We have to talk about quantum nature. Okay, quantum stream of photons, right? Fixed intervals, single photons. So now the same thing happens here. We can actually do the same experiment again experimentally. Also, if you can measure, this is basically a gallium arsenide microdisc. Oh, actually, I've taken this from all of these references are taken from Mark Fox's book. I'm sorry, I forgot the reference. All of this is Mark Fox. Okay, the same reference that we have been using last week also. Fox quantum optics. Sorry about that. CUP, right? CUP 2006, I think. All of this is that. Okay. So basically, this is a gallium arsenide disk. It's a gallium arsenide substrate, and there is a quantum dot embedded in indium arsenide. Okay. Let's not worry about how this is made, but this is a quantum dot. Now, when you shine a laser on this, you excite a quantum dot, and you can make it emit a photon. And then you take the output to a Hanbury Brown-Twiss interferometer, and you measure the G2 function. When you do that, you discover that at time delay equal to 0, you see a sharp dip. Essentially, this dip here at t equal to 0, dip indicates single photon source. Why am I saying single photon source? What happens if there are 10 photons emitted at that pulse? G2 will never be 0 or less than 1. G2 will never be less than 1. Will always be greater than 1 because it becomes bunched light. Only when you have stream of single photons, then you can have G2 function going less than 1. That's why. Okay. You might even ask, what does a negative delay mean? Well, that's a little bit of, it's okay. You just, this basically results from measurements. So you never usually, you send pulses and there's a certain periodicity associated with it. Because of the way we do these measurements, it turns out that you have this. Essentially, this is a reflection of the, if you send, let's say 1 nanosecond pulse stream and keep measuring these delays, of course, you're not going to go from 1 to 100 nanoseconds. Okay, let's take the periodicity to be 1 nanosecond. Okay, then we keep delaying it by 1 to, in steps of 10 picoseconds you delay. What happens if you delay by a certain, 20 nanoseconds, 15 nanoseconds and so on? It can be counted as negative delay in the next pulse cycle. So you are thinking of basically, okay, you are thinking of this, okay, sorry. You are thinking of a pulse like this, another pulse like this. Now, if you measure this delay, this let's say is 10 nanoseconds periodicity. Okay. When you have 10 nanoseconds and you're measuring it, but let's say if you delay, now you're delaying it, right? So the delay is now, this measurement is basically at this point, this point, this point, this point. As you go to very, let's say delay, in this case, I'm increasing in steps of 100 picoseconds, let's say. I'll make measurements. After this pulse, measure here, measure here, and so on. 10 times you're measuring between those 1 nanosecond time interval, you're making a measurement 10 times. The 10th measurement, when it's very close to this one, next pulse, it's effectively like the measurement happened before the next pulse. So it looks like a negative delay. It's just a measurement artifact because we are dealing with pulse source. Okay. So yeah, and these single photon sources, we understood how. I mean, just basically keep, in this case, a laser is triggering them, and you're controllably doing it. So there are single photon sources that are demonstrated with optical pumping, and we also like to do that with electrical pumping. So that's something, that's very, very interesting, because there are a lot of applications in the quantum key distribution and so on. Okay. So we will talk a little bit about the applications of it, but any questions about this? Okay. So this is, this experiment was done probably in the late 80s, the first time. It's been 20, 30 years already. And now it is kind of routine. So actually, if I told you about the nano laser work, right? I mean, nano lasers, how we are trying to make them emit faster and better and all that. One of the demonstrations of lasing is going to be this coherent G2 function. Is G2 of 0 equal to 1? Or is greater than 1? If it's greater than 1, it's not really a laser, it's simply a amplified spontaneous emission. But it just turns out that in experiments, it's easier to see amplified spontaneous emission. So nowadays they insist. And at some point, one of these journals published a checklist. If you want to submit a claim saying that we are actually publishing laser related work, they want you to answer the checklist. Because initially there were a lot of claims saying that everything is lasing. See, the thing is, lasing has signatures of the narrow line width. So initially people said, oh, narrow line width, I'm having a laser. But narrow line width is not necessary condition. Because if I have a cavity which is sharp enough, my photons will emit into that. The density of states is very high, they'll preferentially emit into that. You can get a narrow line width, but it doesn't mean they're coherent. The coherence can only be checked by G2 function. So in nanophotonics area, now you'll find hundreds of papers on these things. Ideally, they should be measuring coherence, G2 function. Okay. So yeah, that's about what I wanted to talk. And so that's it. So in the next lecture, I'll start talking about how to quantize light, and we will talk about what are called as coherent states. So a lot of interesting things. I mean, a lot of counterintuitive things. I see some of the comments that I'm getting on the, online, that some people are asking me, oh, is there any textbook and so on. So, there is no single textbook. I told you that right in the beginning. So it is, frontier research area. Textbooks are yet to be written. Okay. There are some books which talk about different aspects of it, and we are integrating all of that into one course. Okay. And more or less, don't worry too much about the problems and all that. Try to understand the conceptual things. The assignments also, we try to give you some problems just to try to make you think about the concepts. Our goal is not to really try to make you work hard and, solve tons of problems. In this area, I think it's more important to understand the concepts. Okay. So I hope that, you're liking, and if you have any issues, please, write to me directly also. We are of course monitoring the forums, but if you write to me directly as well, I'll try to help you out. All right. So yeah, thank you so much for your attention. We'll see you in the next lecture. Bye.